In this video, we're going to be looking into the effects of temperature changes on the rates of reactions. So we established on the first day of class that temperature is really a measurement of the kinetic energy of particles, or more specifically of the average kinetic energy of all of the molecules in a system. So higher temperature means more kinetic energy. More kinetic energy means collisions are more likely to be successful. We also established that higher temperature meant faster moving particles, which leads to a greater number of total collisions. And both of these factors lead us to a greater number of successful collisions between molecules, which gives us a faster reaction. So in general, at a higher temperature, reactions tend to proceed faster with a greater rate. So before we can get into the specifics of how temperature affects rate, we need to talk a little bit more about activation energy. The activation energy for a reaction is the amount of energy required to create the transition state from the reactants. In other words, it's this distance right here in a graphical representation. So it's how much energy you have to put in to get from your starting point at the reactants all the way up to the top of the peak to the highest energy structure formed in the course of the reaction, which is your transition state. So every reaction has an activation energy, regardless of whether it is spontaneous or not, or endothermic or exothermic or anything else. All chemical reactions have some activation energy. And spontaneous or non-spontaneous, any of those thermodynamic things have nothing to do with the size of that activation energy. The size of the activation energy is, however, related to the speed. In general, a small activation energy tends to correlate to a fast reaction, while a large activation energy correlates to a slow reaction. So that should maybe make some sense, since molecules have to collide with sufficient energy in order for a reaction to occur. If that required energy is really, really big, only a few molecules are going to have it. But the way we can change that is by changing the temperature. The higher the temperature, the more energy the molecules have, the more of them are able to get up and over that activation barrier. And it's important to know that for a given reaction, the activation energy is constant. It never changes. But the rate constant actually does change with temperature. So as you're changing the temperature in a reaction, you change the rate by changing the rate constant. And there is, of course, a mathematical relationship between the rate constant and the activation energy and temperature for a given reaction. And this is known as the Arrhenius Equation. The Arrhenius Equation says that K, the rate constant, is equal to A times e to the power of negative activation energy over R times T. So K is the rate constant. A is what's known as a frequency factor. A frequency factor is a constant for a given reaction, and its purpose is kind of to account for the orientation factor in collisions. A relates to the likelihood that a collision will occur with the proper orientation. So the less likely it is, the smaller A is, the more likely it is, the bigger A is. EA is the activation energy. R is the universal gas constant. In this case, we're using it with units of joules per mole Kelvin, so the value is 8.314 joules per mole Kelvin. And then T is the temperature in Kelvin, and it must be in Kelvin. Degrees Celsius will not work. The Arrhenius equation is most commonly used to calculate the activation energy for a reaction. So usually you don't know the frequency factor for a reaction, and if you're doing any kind of meaningful research where this reaction might not have been done before, the frequency factor isn't going to be something that you can go look up. There aren't really very many frequency factors that are well established, so that means in order to use the Arrhenius equation to calculate activation energy, you have to know the rate constant at least two different temperatures. So let's say we run some experiments and we determine that at 25 degrees Celsius, the rate constant for some reaction is 0.54 inverse molarity, inverse seconds, and at 45 degrees Celsius, so we increase the temperature, the rate constant has increased to 2.04. From just that information, we can calculate the activation energy for this process. The easiest way to approach this type of problem is to start with the Arrhenius equation and do a little rearranging until we get something that's in the form of a straight line. If we simply take the natural log of both sides, we get that the natural log of the rate constant is equal to the natural log of A plus negative activation energy over RT. From there, just writing it in a slightly different way allows us to clearly see how this is now a linear equation. So we have the natural log of the rate constant as y, m, the slope, is equal to negative activation energy over r, x is 1 over t, and the y-intercept is the natural log of a. The interesting part of this for us is that the slope of this straight line is equal to negative the activation energy over the ideal gas constant. And since we know the value of the ideal gas constant, if we know the slope, we know the activation energy. The slope of any straight line is always the change in y over the change in x, and in this case y is the natural log of k, and x is 1 over t, so using the two data points we're given, we can calculate the slope of this line, which will allow us to calculate the activation energy. And when we plug in all of the values that we're given, we're left with something that we can easily solve for the activation energy. So after we round to the appropriate number of significant figures, we find that the activation energy for this process is 52,000 joules or 52 kilojoules. So now I've got a bit of a challenge problem for you to try on your own. For the same reaction in the previous example, how long would it take for 54% of reactants to be consumed at 65 degrees Celsius? So you should pause the video here and try this out on your own, but if you get stuck and need a hint, let it play a little bit longer. So if you need a little guidance, these are the general steps you should take in solving this problem. First, you need to calculate A, the frequency factor, using the Arrhenius equation. From the previous problem, we know the activation energy, and we know K at two different temperatures. So by choosing a temperature and a K that matches, we now know everything except the frequency factor, so we can solve for that. Then you need to find K at the new temperature, at 65 degrees, using the value of A that you found in step 1. And then lastly, once you know K at the proper temperature, you can use an integrated rate law to find T. Pause the video again to go try it on your own, or continue on for the full solution. So the first step is to calculate the value of A. So using the Arrhenius equation, we can solve for A as long as we know everything else. In the previous example, we found the activation energy, and it was 52,000 joules. From the data we were given, we know K at two different temperatures. R is a constant, so we always know that. So you can choose either of the two temperatures as long as you use the corresponding K. I chose to use the 25 degrees Celsius case, so when we convert that to Kelvin, we get a temperature of 298 Kelvin. And the rate constant associated with that was 0.54. So when we plug all of that in and solve for A, we find the frequency factor for this reaction is about 7.039 times 10 to the 8th. So for the second step, we need to find the new rate constant at 65 degrees Celsius. Now that we know A, the frequency factor, and we know the activation energy, we can plug in any temperature we want to find the new K. So now we can plug in everything we know the frequency factor, and we know the activation energy, and R is a constant, and put in our desired temperature, 65 degrees Celsius or 338 Kelvin, in order to find K. And we find a value of K at this temperature of 6.473 inverse molarity inverse seconds. So the final step is to actually calculate the time it's going to take for 54% of our reactants to be consumed. In order to do that, we need to use an integrated rate law. To know which one, we need to know the reaction order. But since you were given values of K, including units, of inverse molarity inverse seconds, you know that this has to be a second order reaction. So we need to use the second order integrated rate law. So in this problem, T is the variable that we're looking for, and K we just calculated in the previous step. We're not given exact concentrations in the problem, we're looking for a percentage remaining. So you're asked how long it will take for 54% of the reactants to be consumed. So for the ease of math, let's make the initial concentration 1 molar. If 54% of your reactants have been consumed, that means 46% remain. So your concentration at time t is 0.46 molar. And once you plug in all of those values and solve for t, you should find that the time it takes is 0.18 seconds.